to approximate how close we are to what we're trying to approximate. We're going to see how close our approximations are. So first we're going to do that two easy ways, geometric and alternating. So there are three, well, that's the second. So up until now, we just found out what values we're like allowed to use the series for. Now we're going to actually use the series. So what's the purpose of a series?
Power series.
Power series.
Approximate function.
Approximate function. So now we haven't actually done that yet. So now we're going to actually approximate a function and then see like how close our approximations are. So what's coming next? So we're going to find out how to find an error bound for a series in general, not just the easy way. We're still alternating in geometric.
Can we start every lesson with these?
Yeah, I agree. Okay. So let's find the series for x times sine of x, that x equals 0, and then use it to approximate the value of f of negative 0.1. So you can create the series for this either like from scratch, or you can use what you know about the series of sine already. Do you have that memorized?
Wait, F? F over...
Yeah, so we have to decide whether, you know it's odd or even. Remember that whole thing?
X minus x cubed plus x, right?
Yeah, so now the graph of sine, is odd. Meaning that it's symmetric over what?
The origin.
The origin. So if I flipped it this way and I flipped it that way, it would still be the same graph. So I know that it's an odd graph. We're this thing too. So if that's true, then it's odd.
Wait,
So if I plug this number into sine, and I plug in the negative and make my answer negative, I get the same value.
Okay.
So sine is odd. So that should be your clue that what's the series for what is sine of x equal?
X minus x cubed over 3 factorial plus x to the 5th is 5 factorial.
How did you not start with 1?
The sine of 0 is 1. The sine of 0 is 0.
Okay, that's fine. Thinking about it. All right. So now that that's a series for sine, what's the series for x times the sine? Everything multiplied by an x. So x times the sine of x equals x squared minus x to the 4th over 3 factorial plus x to the 6th over 5 factorial and so on. So now even, but it's not the same function, so that's okay. So now let's use it to approximate the value of negative 0.1. Plug negative 0.1 in. Good. So plug negative 0.1 into that. Do it on your calculator.
I thought you said our calculator.
You know what? You did that.
Happy gal.
I need to bring my calculator. I have two if you want. Like a true one. I have two.
That might be intense, sure.
I won't
Not
have
sharing
that.
one.
I'll be another.
Don't change that color scheme.
Change the color scheme.
One's the-
I don't know.
Do you have any batteries and stuff?
No, I don't. Sorry.
What's the factorial?
Factorial things above. No, I lied.
No, it's not listed on there.
It's in the catalog.
That's an exclamation point or factorial?
No, it's not listed like on the calculator, but
I think it's listed as
one
explanation point. I think it's in. I don't know what it is.
box. Yeah. No, it's something.
What's 3 factorial?
6.
6. It's 5 factorial.
16.
Forget it. 40?
20?
120.
I think that's just really small.
Well, I mean, it's going to be really small.
Yeah, but I don't even know how to write that. It's like even the negative 9.
Do you know that alpha 7 is the log, like regular log?
Yeah.
I didn't know that.
I know that. Alright, so what is this side? Did you all get 1.6667 times 10 to the negative 9th?
I didn't plug it all in.
Wow.
Sure, let's go.
We know. What's the answer? Just plug it all in. Do it all in one
Wow.
window screen. And just hit
There it is. It's hard though. It's alpha division sign.
Good call.
That, is that the answer? No.
No,
What's
that's
the
like
answer?
I've never seen a button.
Oh,
No.
That's
Point
what
nine
Alpha
nine
division
eight?
sign equals the factorial sign.
equals 20 of 998.
you get that.
See, look.
That?
Yeah.
You didn't get that?
Now I know what I did wrong.
Calculator somehow.
Nope, I still don't know what it is.
I didn't get a negative, but that's
I didn't get negative.
Just
I didn't, that's equals.
Oh, okay.
That's, you got a positive, right? Did we all get that? Are we sure?
That's right.
Yes.
Okay.
I don't understand why. Did you
Ron, look at his calculator, see what he did wrong.
Everything.
This is one.
It's
It's one squared.
No, it's
One
gross
point-
inaccurate.
point one, found it. There you go. Got it.
Alright, so now let's see, so is this our approximation or is that the actual answer? That's our approximation. Okay, so now let's see how close were we.
How close were we?
It's pretty. No, it's
How do you know how close you are?
Now we look at
Just plug it into the actual,
We were pretty freaking close.
it's grossly inaccurate. But
okay, so
We got a
negative
pocket
0.1 times the sign. Make sure that you're in, your gradients, right?
It's not gonna be, it's gonna be negative.
yeah, it's negative, and
Why
it's
would
not
it be
even
negative?
close. You're off by like
Because
a
you're-
factor of
because you're
10.
multiplying it by negative. So what?
No, but you're off by like a factor of 10.
They're all gonna be positive.
I don't
I
know where I
got
got
the
that.
same thing. We had the same thing.
Yeah, so did I.
I got negative 0.0998.
Positive.
I'm going to put more
Your
decimals here
biggest
because
term's
it's close.
That's positive.
This is 0.00998333417, right? And if I do this, I get the same exact thing.
Wait, what are you doing there? Just take it.
Negative 0.1 times the sign of negative 0.1.
That's so weird. It's off by a factor of 10 though.
You forgot to multiply by negative 0.1.
That would do it.
That would be positive 0.01.
Would be
Alright,
10.
so our approximation is like perfect. I didn't mean for that to happen.
You're just the best.
No, I should have picked a number further away.
That's cool.
Well, we could just chop off the x to the 6 over 5 factorial. That'd be close.
It's kind of interesting too. Let's do that. Take that out and then do it. That's gonna add such a small thing now.
I'm not.
Well,
Just hit like second entry in your calculator and just do that. You redid it all?
Yep.
top of division.
So what do you get then?
983.
So this is, it should be 3, 3, 3, 3. Did you get that? I think one too many.
It's just threes.
Whatever.
Okay, so then this is actually 0.00998333417. So that extra term made it more accurate. So if we, which makes sense, good. So if like we went out, if your calculator had the ability to give you more decimals, you would be able to see that it's not, these two aren't equal to each other. But if I needed to be more accurate, I could always just add more terms.
But you're close. So like so close to the center though. That's probably what it's
Exactly. So the reason why this is very accurate is because I'm very close to the center. Okay? So now we know how close we were. So let's subtract these two to find out our error.
Well, I'm gonna put zero.
Just gonna put 0.
Well, yeah.
Your pet's misleading because it's not perfect.
I didn't-
Yeah, I agree. It is misleading. So
Okay, so
if I just, if I
0.00000001.
if I compare these two, meaning that I subtract them, I do this minus that, I
What's
get
zero?
1.499 times 10 to the negative fifth.
Is there a
So,
so that like
zero?
like an infinitesimally small number? Like you're not saying it's 0, but it's like infinitesimally small.
Zero.
But it's not 0. Like
Is
you
there
want to.
like a proper way to write that?
No, I just wanted there's notation for it.
I don't, not that I know of, but I'm sure that there is.
1.2 times
So it'd be
10 to the
like-
negative 1 million.
1 times 10 to the negative 50. Like that would be
Yeah.
infinitesimally small.
But then you have to
No, I
use
don't
low
think you
tall.
can say that. Then you should use the tall, would make sense. All right, let's try another one. All right, so let's find the series for ln of x about x equals 1, and use it to approximate the value of f of 1.0. So do you have, like, is ln in your chart?
I
Yeah.
believe it is, but
ln of x plus 1 is in your chart. ln of x is not in your chart.
So you have to make minus one.
you can't do that right
that.
now.
But so let's build this one from scratch, just for fun.
Okay.
So what's f of 0? Oh, I'm sorry, not f of 0. F of 1, right? We're not centered at 0 here, we're centered at 1.
2x minus 1.
0.
We do once we're building our series. We're just trying to like figure out the derivatives at the center. So f of 1 is 0. So let's find f prime of x.
1.
Let's just find it of x first. Let's not plug 1 in yet.
1 over x.
1 over x. So f prime of 1 is 1. What's f double prime?
Negative x to negative 2.
Yeah, if you want to write this as x to the negative 1, this is negative 1x to the negative 2.
Negative 1 over x.
Yeah.
So f double prime of 1 is still negative 1. Good? Alright. Polka dot zebras.
Oh.
1 over x. That's right.
So this is
I don't think you said 11. No.
polka dot zebras.
Okay, now I understand.
2x to the negative 3.
Everything makes sense.
So now that's, what's that? 2? So I didn't
But I got the
tell you
equal
how
one.
many terms we wanted. This is enough terms. Let's try that.
Still 1 more.
No more?
No, absolutely
No,
not.
no more.
Yeah.
Always go.
Too many polka dot zebras.
I don't want to do another one. Okay, so here
Thank you.
we're saying that ln of x is approximately equal to. Why isn't it just equal to?
Because it's an approximation.
Because I'm only using the third order. If I did it forever, it would be more. Okay, so now here, this is approximately equal to what?
0 plus
I want to clear.
1 over x. Do it. I know, but I was gonna do times x.
Plus x.
It's 1 over 1 factorial times x minus 1 to the 1.
Oh, I said 1
You
over
said
x.
1 over x. Yeah. The next one is negative 1 over 2 factorial times x minus 1 squared. See, I don't even have to do this. The thing is that one.
Bad excuse.
Alright, so now, what's my last term?
2.
So, are you alright with that? Okay, so now, let's approximate. Use this to approximate f of 1.2. What is it? What do I do?
Plug it in.
1.2.
Plug it in.
So what you get, check.
Oh.
So do you kind of see how the whole centered at 1 thing works? Like when I plug in a number close to 1, all I get for my powers is the deviation from my center. That makes sense? If I get 0.2, when I plug, that's going to different powers because I'm 0.2 away from my center. Alright, so do I have to do this too, or center strings?
What's next? It's not 12, it's 1.2.
1.2.
Sure.
Answer is 7.
We got 0.18, which is probably good, right?
Yeah, I just plugged it in. Wait, my question is, why do we need to approximate it
If we're plugging it in,
if we can
calculator
just,
anyway.
yeah, if we can just
I know,
plug it in?
it's really.
I totally
Because
agree.
if this were
you're
hundreds
using a
of years
calculator
ago-
anyway, then this is kind of silly. But back before there were calculators,
Well, no one knew how to do LNs before calculator.
no one knew how to do ln. Like it's not like you
So
like
just
you
put it
can
on.
if you needed to.
Was that one?
You could plug 0.2 into this by hand if you needed to.
I could, but I mean,
It's real,
But
but
you
like,
can't just plug 1.2 into ln and like know what the answer is. There's nothing to do to know
it's
what
just
the
guess and check, right? Because it's like,
guess and check
e to
what.
what power equals
Yeah.
that? So you have to like literally check every single
And
one.
E is irrational, so it's
Yeah.
How long has E existed?
good question. I don't know. I mean, how long have we known about E?
Yeah.
I don't know.
Right after D, right after D was invented, you know. Right after D.
All right. So did you guys get? Did you get 0.18266? Good.
yeah, and
No,
then
this is
the actual, do you want to know the actual?
Yeah. So what is the ln of 1.2?
0.182322.
That's fine.
Okay. So let's like make sure that we go at the same amount of decimal places. So I'm just gonna put another 6 here. Just
It's a 7. Rounds up.
Fine, you can round it up.
Not very accurate.
So now, what is our error?
Like 0.00345.
0.000345. Yeah, Karen got it.
I wish I could add.
Good? That's our error.
So exciting. How close were we? Pretty close.
It's kind of grossly inaccurate.
It's not grossly inaccurate.
What's our percent error?
What would happen if they built a space
Yeah.
shuttle with that kind of?
Wait, Ben,
It
find
would
the
have blown up.
find the. They're not going to approximate for the space station.
Well, then why?
Well, who
They
else
would
do
use the fourth term.
At least.
That's what I said. Go one more.
All right, so now I just wanted to do some theory with you. So this is how we write just a general Taylor series.
Wait, is it a cool thing? you're talking about?
Look at
Oh no, it's actually Taylor.
No, it's actually Taylor. Why do you know it's Taylor, not Maclaurin?
Because it's
Because there's a center
This
that's
is
not
next
zero.
line side. Yes.
1618.
Oh, great to know. Okay, so here, this is our polynomial that approximates our function. So I think that all of this you've seen before, except for that.
Yeah, that's
What is that thing?
So instead of just doing ... they're telling you that
your last
they're giving you this r sub n thing. So if we continue our series forever, the series equals the function over the interval of convergence. So over your interval of convergence, which we learned how to find previously, we know that this function actually equals that polynomial if we went on forever. Like if we found infinitely many terms of our polynomial. Kieran, or not Kieran, I see you.
Right now.
Right, so in practice, we only use the first few terms. So the terms that we don't use is called our remainder. So if these two actually equal each other, if our function actually equals the polynomial, then what the terms that we don't use is how far off we are.
That's our error.
That's our error. Does that make sense? I feel like that's
Bring
kind
it
of hard.
to
R sub n
You add your
is,
error.
Well,
yeah, if you
obvious.
added your error, you would have it right. If you took your approximation and added how far off you were, then you would have the right answer. The problem, or subtract, then r would be negative. So now the thing that's hard about this is that you often don't know what the error is. If you knew what the error was, then you don't have an error. You could just add your error and it would be right. So if we knew the size of our remainder, then we know the size of our error, which means that we know the real answer. So what we're going to do, because I know that we have a calculator and we can always just plug the number in and that's fine. But what we're going to do is learn how to approximate our error if we weren't so lucky to just be able to plug numbers into ln or sine or whatever. We're going to learn how to approximate our error. So here are the possible things that could happen when we approximate our error. So with our calculator, it's easy to tell what the error is because you know what the real answer is supposed to be.
You put a frowny face instead of a dot.
I didn't have.
Because it's not
I
really.
didn't have.
It's not sad.
Do you not know making that a photocone on a computer?
No, I don't.
It's literally the other parenthesis still.
Oh no, I got this from the Magic Pen.
Oh.
See how there's
Oh,
a
the one that
Magic
like
Pen?
you really get it
Wait,
right.
recognize the shape.
Creative Pen.
Quite good. No, it makes like smiley
You can
faces.
pick a smiley face.
There's no frowny face. Wait, click. Yes, there is.
There's
Oh,
not a
wait, hit
frowny
the arrow.
face. You don't think I checked? Come on.
Wait,
I
you.
don't.
So.
erase that?
Shh. No,
Oh.
I can't.
Wait, if
So-
you flip your pen around.
Stop. Because we know the answer, we're not trying to approximate. If we didn't know what the answer was, finding out how close it is more complicated. So if you can just plug a number into ln, it's easy. But assume that you can't. It's harder to find out what that error is. Like, how did people before there were calculators that you could just plug a number into ln of 3.7? You could just do that. How do they know how close they were? So these are the three ways to figure out how close you are. The first way is if it's a geometric series. If it's a geometric series, it's painfully easy. If it's an alternating series, it's also painfully easy. If it's any other type of series, it's not.
There's no such thing as painfully easy.
So, we're going to learn these two today, and we're going to learn that one tomorrow on our half day, of course. That's how it felt. Okay. So, geometric series.
Logic.
Yeah. We're going to see our two days on that. So we have a formula for the sum of an infinite geometric series. Oh, I guess that's right. So the error is easy to calculate. We just calculate the sum of the terms that we didn't use. So you know what's the formula for the sum of an infinite geometric sequence? Yeah, remember the formula for the sum of a geometric series?
Oh, A over 1 minus R.
A over 1 minus R.
Let me go.
So the sum of an infinite geometric series, so A, that's not necessarily true, A times R to the N. Start at 0, or you do it last one. So this series always equals A over 1 minus R. So you don't have to approximate, you can just know the sum. So if we just take the sum, like if we use the first 5 terms, then we can just find the sum of the 6th on, and that would be our error. Make sense?
Yep.
You just use your A as the 6th term. R is still the same. So here's a little example. So if I have 1 over 1 minus x, that's assuming that the A is what? What's my first term?
1.
1, and what am I multiplying by each time?
R,
X.
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 Well,
Which is
equals
what?
R.
So here, my R is x. So here I'm multiplying each of these by x. Is that okay?
Yeah.
So it's just the sum of x to the n, starting at 0 to infinity. So if we use the first 4 terms to approximate the value of this function, then I do 1 plus x squared plus x to the 4th. And then what's the first term I don't use?
X to the 5th.
X to the 4th. Then my R is still the same. I'm still multiplying by x each time. So to find the error, to find the rest of these, I'm just going to take the 4th, x to the 4th, and then find the sum of them.
Okay.
Let me tell you what I mean. So the A over 1 minus R,
I know that was a page.
A over 1 minus R is now my first term. The first term of my remainder is x to the 4th.
So that was
And I'm still multiplying by x each time. So this is my remainder.
That was 1 term, your remainder. There's infinite.
It's
The
not
sum.
1 term, this is the sum of
Oh, right,
those
right.
terms, right? This is equal to x to the 4th plus x to the 5th plus x to the 6th and so on. So now plug your x in. I plug 0.2 in,
going just to find the remainder.
just to find the remainder.
Oh.
So often the AP test tells you to find the error of a series, and they give you an alternating one, or they give you a geometric one, and I feel like maybe people don't focus on the easy ones because they're easy. So I just wanted to take a whole day to just do the easy ones, because I'd say more than half the time they give you the easy ones, and people try to do this whole long, complicated process the not happy way for the easy ones. So don't do that. So what do you got? 0.002 what? That's it?
That's 0.16 over 28.
Alright, so that's our what?
Remainder.
That's our remainder, which is another way of saying our
Error.
error. So now let's see if that actually worked out. So let's take 0.2 and plug it into the first 4 terms. Into these first 4 terms. Plug 0.2 into that, see what you get.
2.8. 2.4.
Or you just
That's 1.248.
Yeah, I get it.
1.248. So when you add that in, you get 1 point. So this is our approximation. Using the first 4 terms of that series. We found that 0.002 is our error, starting from the 5th term, which is actually 4th on.
This was
So
perfect.
what do you think our answer actually is?
1.25.
So let's plug 0.2 into that, see if it is that.
1.25.
Yeah, so you do 1
Good.
over 1 minus 0.2, you get
Probably not.
1.25, which is the right answer. Is that cool?
Is it always perfect?
It's always perfect in geometry.
Oh, that's awesome. Yep, definitely worth it.
Why are we?
Great today.
Check some for issues.
Bye. Have fun.
Not an overcomplicated way to do things. That
Okay.
sounds like a great day.
Alright, so one more example of this. Alright, so when we use a Taylor series to estimate the value of a function, the end of the series that we do not know is called the remainder. If we know the size of the remainder, we know how close our estimate is. So now let's just do it with a different geometric series. Instead of, similar to the previous one, instead of multiplying by x each time, what am I multiplying by? Squared each time. So for this, let's try to use this to approximate this over negative 1.1. So let's just find out a formula for our error.
Wait, is it -1 to 1 or is it -1 to 1? Because that's a common.
That's telling you when it converges.
Okay.
This series converges to this function over this interval,
Also known as the interval convergence.
also known as the interval.
Boom.
So that means that this will work. This will approximate this anywhere in there. If I try to plug in like 1.5, it won't work. It won't converge.
So
These two
we
don't equal each other.
expect to work backwards using like when we use the ratio test to find the radius of convergence. Do you have to like do that but work backwards?
No, I don't really know what you mean.
Well, do you know how we found like the interval of convergence
Yeah.
using the ratio test?
Yes.
Well, do you have to like now manipulate the one side so that it only works between -1 and 1?
No. No, like they're just saying that they already did the convergence problem. They got that as the answer. So don't plug in a number outside of that range. That's all they're saying. I don't know if I really get your question.
No, it's kind of a bad.
Plug in 0.
You can
Yeah.
you can plug in 0. 0 would be easy. Plug 0 to that. Plug 0 to that. Easy. It's always exactly equal at the center of your interval. Okay. So anyway, let's just find an equation for our remainder. So our remainder is what? What is the first term I don't use? X to the 8th. And what am I multiplying by each time? Squared. So now this is a formula for my error for any x in that range. So if I want to figure out how close I was if I plugged in 0.2, I can plug 0.2 in. If I want to figure out how close I was when I plugged in negative 0.8, I can plug negative 0.8 in.
So if you pick 0, there's no remainder. So does that mean that the estimate for the approximation is perfect?
Try it. Plug 0 into that, plug 0 into that, you get the same thing.
Yeah, it's plus 0.
So it is perfect. It's always perfect at the center. Remember how we talked about, like,
Oh, yeah.
back in the beginning, like, the 3 scenarios of convergence? It could either converge over all values of x, so that our radius of convergence is what? Infinity. It could converge over interval, or our radius of convergence is some constant, or it could converge only at the center. So our radius would be 0. It always converges there. Good? Done with that. Now let's talk about alternating series estimation theorem. So this is also very easy. So it's not perfect though. In the geometric series, your approximation for your error is not an approximation. It's what the error is perfectly. So for alternating series, it's not that way. It's just an approximation, which is really all you can hope for. The only type of series that you have a formula to find the entire sum is geometric. Every other type of series, it's just an estimation. So for a convergent alternating series, the truncation error, meaning that like if I don't, like whatever terms I don't use, whatever terms I truncate at, is always less than the first missing term that has the same sign as that term. Do you want me to say that again?
Yes, please.
Right. The truncation error is less than the first missing term. It has the same sign as that term.
What's truncation?
Truncation means like where I cut it off.
So you plug in the next number, and you know it's got to be less than that.
You find the next term,
And it's
Yeah,
the same,
and you plug the number into that. It has to be less than that.
same sign as the last term that you find.
So for example, let's say, is this my last slide?
No.
Oh, good.
You have
Alright,
it.
so let's say I had negative 1 to the n over n. Is this a convergent alternating series?
No. No. In nature.
It is harmonic, but it's an alternating harmonic series, which works. Remember, to test whether or not an alternating series converges, you just take the limit of the absolute value of the terms. And if the limit of the absolute value of the terms is 0, then the alternating series converges. It's kind of like the converse of the nth term test, but it actually works. But it only works with alternating series.
No, I thought the harmonic series diverged.
The harmonic series diverges, but the alternating harmonic series converges. So if I do 1 minus a half plus a third minus a fourth plus a fifth, that converges. If I just make the 1 pluses, it diverges.
Oh, the alternating series says that if it equals 0, it converges. Right?
Yes.
Okay, sorry.
It's okay. Alright. So are we good with this? So we just had to see this visual before, but I don't know, I just feel like we didn't really talk about it enough and we didn't really get it. So, you start at 0. You add the first term on. So what does S sub 1 mean? What is that notation referring to?
Whatever your first term equals, like whatever.
It's like a partial sum of the first term. And my next term is going to be negative. Right? Positive, negative, positive, negative. So then my next term is going to subtract. But because those terms are getting smaller, it's not going to bring me back past 0. I'm never going to get past this first red line. And then the next term is positive. So, but it's smaller than the previous term. So I'm going to add it on, but it's never S sub 3 is never going to surpass S sub 1. What does S sub 3 mean?
Partial sum of the third term.
Partial sum of the first 3 terms. Good. Now the next term's negative. But because the limit of those terms is 0, these terms are getting smaller. So I'm going to subtract, but I'm not going to get past S sub 2. Because the terms are getting smaller. So then I'm going to add, and the next term would bring me, I don't know, somewhere here. But S sub 5 isn't going to be bigger than S sub 3. And that's how I'm going to like zero in on my limit. Does that picture make sense to you?
Yeah.
It's a good picture.
That's a good picture.
Well, thank you. I stole it from the book. All right, so now, if you can look at this, the error, how far off I am from the limit, from the L, is never going to be more than what the next term is. Like the distance, like how long this line is always going to be more than the line of where you were to the limit. Say
So
that
you
again?
need to plug in the next term and then just, like I said, an inequality. Like,
Figure out what the next term is.
Yeah.
That term has got to be bigger than how far you're off. Meaning that this green line is bigger than this little green line. The next term is going to be more, is going to like overshoot you from that limit. And then you're going to subtract and go back and back and back and back and back and back and back. So that's why.
all you can say is that it's less than what the term is.
All you can say, that's a bound for your error.
Yeah.
To let you know that your error can't be more than that. It's going to be smaller than that. You just don't know how much smaller than that it is. And that's all we're trying to do here. We're not trying to find exactly what our error is. If you could find exactly what your error is, then you know the answer. So it's not even an approximation anymore. We're just trying to find a bound for our error. Our error is not going to be bigger than this. So you know how accurate, you can't be more wrong than that. Okay, so let's try an example. What? Okay. So here is an example of an alternating series, sine. Did I steal this from the book?
Oh, I said McLaren's fault.
I spelled it right.
McLaren fault.
So let's use the Maclaurin series of order 5 to approximate the value of sine of negative 0.3. And please give a bound for the error. So now here we're using order 5, meaning that we're using the fifth derivative, that term. So how many terms are we really using?
3.
3. These 3. So I'm taking negative 0.3 minus negative 0.3 cubed over 3 factorial plus f. Or the negative 0.3 to the fifth over 5 factorial. Everybody want to do that? Okay. Now, whatever that answer is. Yeah, it looks like Christine's doing it. Is she? Are you doing it?
Yeah.
I forgot the radio air. It's quiet. Is that the microphone?
Yes.
No.
Okay. So now, whatever answer we get for that, we're going to see how close that answer actually is by using the alternating series error approximation. So let's try to do that first while she's calculating. What's the first term we didn't use?
So the seventh. Over the
Negative
seven.
0.3.
It's negative x to the seventh,
seven.
right? So our error estimation. Just yell out when you have it, Christine.
I think it's -.29552.
Negative 0.2, I didn't hear you. What?
29552. 25.
Okay. So our error estimation is just the next term, which is negative x to the 7th over 7 factorial. Plug negative 0.3 into that.
But you don't use the sum anymore?
No.
It's not a geometry.
All we're just saying that the next term is bound for our error.
Dyslexic drops.
Okay, so when Max plugs negative 0.3 in, watch your language, it's negative 4.
Reaching point positive.
That's right. It sold me at the ear.
No. Oh,
What's this next one?
yeah, I think that, like, you're going to plug negative 0.3 in,
It was.
and then there's a negative UH. For negative, I'm sorry, 4.33929 times 10 to the negative 8. Right? So that's pretty close. That means that there's how many zeros?
7.
7. Good. It's good. No, we're not even that. I mean, we're close. We're not that close. to
I
the
don't
7.
understand what that means.
So what we're saying is that our error is no bigger than that. So let's find out what our error actually is to just prove to you that this works. So what is the sign of negative 0.3? Which we're probably going to have the exact same thing because we're not able to get more than 8. Kristen, and I think, are you?
Not on it. Get
-.29552 or 202067.
through span there.
So now subtract, do that minus that.
-4.333866.
Oh, wait, hold on. Sorry. So the actual. Sorry, go ahead.
4.333866 times 10 to the negative.
Okay, so that's less.
Yeah, it has to be.
So this is our, so let's go through and talk about what all these numbers are.
So
That's what our Taylor series approximation for sine of negative 0.3 was. That's our approximation. I should, like, use a number so that the kids can see. So this is our approximation of what sine of negative 0.3 is. This is what sine of negative 0.3 actually is. This was our error in our estimation. That's how much we estimated the error was going to be. This is our bound for error, meaning that our error can't be bigger than that. This is what our error actually was we were only able to find that because we have a cute little calculator that we can type sine of negative 0.3 into.
So
Back in the day, they didn't have which two numbers?
the bottom one.
This one
And the actual error.
and this one. All they knew was what their approximation was, and they knew what their error bound was.
Alright, so what were you saying about, it has to be the same sign as the first missing term?
Meaning that which one is bigger? Is this bigger or is this bigger? It's hard to look at, right?
That top. So negative.
Actually, it makes sense because the next term.
This one is further from 0, right?
Yeah.
Like, because they're negative. Like, what did
Now
I say?
this one is.
But it's 2025. This is 2020.
That was
This one's further from 0, meaning this one is more negative. So this one is smaller. So that means that our error is this far off in magnitude, but it has the same sign as the term. The term is a negative term. So our error is negative. We were too low. Right, or the actual
So if
answer
we're
was
too low,
bigger.
our error should be.
Oh, so we're going to subtract the negative
Bring it
back,
back.
so that will push you back.
I'm sorry, so your question first.
So our error should be positive, so it should bring it back up closer to the actual.
All we're saying is that, like, we were this far off, negative, whatever that is.
Why did you have that?
Yeah, okay, I got it.
Like the number, like if I plug
That turned into
Negative.
a positive.
negative 0.3 to the second pin, this is a positive number.
That's
Yeah.
But that doesn't tell you, that just tells you the magnitude. You figure out the sign of the error from the sign of the term. Is what the theorem says.
Wait, what is
The sign of
error
that
bound?
term or the sign of like
This is our error bound,
the sign of that term or the first term?
the sign of that term.
Then why do you need the negative?
It just was a negative.
That's zeros, that's why.
No, I'm just so confused on that. Like, if you're judging it by the sign of that term, whether it's like too high or too low, then why don't you just put the negative in and it'll work out either way? Like, you know what I mean? If that was a positive term, then the number will come out positive, and therefore, like, you know what I mean? Like,
If it was a positive, I guess because like this error formula works regardless of what number in the input you plug in. You could have plugged any number in, but that error, the answer is going to depend on what number you plug in. So that formula, this formula works for any number. We happen to plug in a negative. That's the only reason this came out to be a positive. So whatever number I plug in, if I use the first three terms and I plug in I'm always going to have an over or an underestimation. My error will be a negative thing. So now because of that, like this only came out positive because I plugged in a negative. If I plugged in a positive, it would have come out negative.
Because it's on the other side of where it is, because of
Yeah,
that
like I
thing.
think if you like went to this, you would, like we are on this side of our limit.
So it's gotta be positive to get it back up.
no, I get it, because, like, whatever the last term is, like, the last term has to be, you're subtracting something, right?
So
So obviously,
overestimate whatever the left.
yeah, your first estimation was too big, because the next one's bringing you back down.
Yeah.
Same shit or whatever.
That was a little complicated. All right,
That was rough.
so your homework tonight, I don't even remember where it is.
Page 500, number 1 through 5.